In the cosmos's farthest reaches, the James Webb Space Telescope, JWST, has begun unveiling secrets that could reshape our understanding of reality. This $10 billion engineering marvel, orbiting the Sun nearly 1 million miles from Earth, involved over 10,000 professionals across 14 countries. Before we go any further, take a second to breathe. If stories like this make you feel that something big is coming, hit like and subscribe. Tell me in the comments what you think is really happening out there. And if you believe more people should see what's unfolding in the dark, share this video on X, Facebook, Reddit, or in your group chats. You're the reason we can keep chasing the truth. Thank you for staying curious. Designed to probe deep space, JWST reveals not just stunning vistas of galaxies and nebulae, but also anomalies that challenge our fundamental laws of physics. JWST's infrared capabilities. Allow it to see back in time, capturing galaxies that formed mere hundreds of millions of years after the Big Bang. However, strange patterns have emerged, galaxies existing where they shouldn't and stars defying our models of gravity. These aren't isolated incidents, but part of a growing body of evidence suggesting the universe may not adhere to our most advanced theories. Observation. JWST has detected galaxies that formed as early as 300 million years after the Big Bang, surprisingly mature for their age. This challenges the timeline of cosmic evolution and raises questions about early universe conditions and galaxy formation processes. The implications are profound. If the universe defies our current understanding, foundational theories like Einstein's general relativity and the standard model of particle physics may need revision. JWST's observations have sparked debates among astronomers, with some attributing the anomalies to instrumental flaws or incomplete models, while others see glimpses of new physics beyond our current framework. Interpretation. The anomalies could signal phenomena outside our current theories, such as exotic matter or energy, like dark matter or dark energy. Alternatively, they may hint at undiscovered forces or dimensions. Regardless, the universe is clearly more complex and mysterious than we imagined. Speculation. If reality's rules are more fragile than we thought, science's future may lie in embracing uncertainty. Like Hubble before it, JWST could revolutionize our understanding of the cosmos. Its legacy may be in revealing how much we still don't know, showing that the universe is an endless mystery where each discovery leads to new questions. As we push the boundaries of knowledge, we must prepare for the universe to continually surprise us, challenging our assumptions and expanding human thought. Part 1. The Uninvited Guest. The universe has always been a canvas of mystery, but the James Webb Space Telescope has become its most unexpected storyteller. Launched on December 25, 2021, this technological marvel has already transformed our understanding of the cosmos. With its 6.5-meter gold-plated mirror and state-of-the-art infrared sensors, Webb has gazed deeper into the universe than any instrument before it, revealing cosmic landscapes that have remained hidden for nearly 13.8 billion years. But its revelations are not just beautiful, they are unsettling. With each new image, each new dataset, Webb is challenging the laws of physics that have guided us for centuries. Are we witnessing the birth of a new era of discovery, or the unraveling of everything we thought we knew? Observation. Webb's infrared capabilities have allowed it to peer deeper into the universe than any telescope before it, uncovering structures and phenomena that were previously invisible. But these discoveries are not fitting neatly into our existing models. They are forcing us to question the very nature of space and time. In its first year of operation alone, Webb has captured images of galaxies so distant that their light has taken over 13.4 billion years to reach us. These faint, reddish smudges on the cosmic canvas are not mere curiosities. They are galactic time capsules, offering glimpses into an era when the universe was less than 400 million years old. The first hints of trouble came from distant galaxies, faint glimmers in the void that seemed too mature for their age. These massive, well-formed galaxies appeared to defy the timeline of cosmic evolution. Astronomers have identified galaxies like GNZ 11, which exists a mere 400 million years after the Big Bang, yet already teems with a population of stars equivalent to the Milky Way today. Something unseen, something unaccounted for, may have shaped them. The implications are staggering. If our understanding of galactic formation is wrong, what else might we have missed? Webb's deep field images reveal not only galaxies, but also the cosmic web, filaments of gas and dark matter that cradle these galaxies. These structures, predicted by simulations but never before observed in such detail, stretch across millions of light years, connecting clusters of galaxies like an invisible scaffold. Yet the observed mass of these filaments far exceeds the predictions of current models. Dark matter, the elusive substance that makes up nearly 85% of the universe's mass, may be distributed in ways we have never anticipated. Its gravitational influence could be sculpting galaxies and the cosmic web in ways our equations cannot yet describe. Speculation. Could there be a new force at play, one that shaped these ancient galaxies and continues to influence the universe today? If so, it would rewrite not just cosmology, but the entire framework of physics. The Standard Model, which has stood as the bedrock of particle physics for decades, might need to be expanded or even replaced. Webb's observations are not just about distant galaxies. They are about the fundamental forces that govern all of existence. But the mysteries do not end with galaxies. Webb has also turned its gaze toward exoplanets, worlds orbiting distant stars. Its sensitive instruments have detected the atmospheres of these planets, identifying traces of water vapor, carbon dioxide, and even potential biosignatures, chemical compounds that could indicate the presence of life. One such planet, TRAPPIST-1e, located a mere 40 light-years away, has an atmosphere rich in water vapor and a surface temperature that could support liquid oceans. Yet the very existence of these exoplanets challenges our understanding of planetary formation. How did these worlds form in systems so different from our own? And if life exists there, what does it mean for the prevalence of life in the universe? Observation. Webb's spectroscopic data has revealed that some exoplanets possess atmospheres with unexpected chemical compositions. For example, the gas giant WASP-39b, located 700 light-years away, has an atmosphere rich in carbon dioxide, water vapor, and sulfur dioxide, a cocktail of gases that suggests complex chemical processes at work. These findings are reshaping our understanding of how planetary systems evolve and what conditions might be necessary for life to emerge. If life can thrive under such diverse conditions, it may be far more common in the universe than we ever imagined. Yet, for every answer Webb provides, it raises a dozen more questions. The telescope's observations of the early universe have uncovered stars that seem to defy the laws of stellar evolution. One such star, Earendel, located 12.9 billion light-years away, is the farthest individual star ever observed. Its existence challenges our understanding of how the first stars formed in the aftermath of the Big Bang. Astronomers have long believed that the first stars were massive and short-lived, burning brightly before exploding as supernovae. Yet Arundel appears to be a stable, long-lived star, its light shining across the cosmos for billions of years. Speculation. Could our models of stellar evolution be flawed? If so, the consequences would ripple through astrophysics, forcing us to rethink everything from the formation of galaxies to the origins of the elements that make up our own bodies. Webb's observations are not just about distant stars and galaxies. They are about the very fabric of the universe and the laws that govern it. As Webb continues to peer deeper into the cosmos, its revelations grow ever more profound and unsettling. Its images of the pillars of creation, towering columns of gas and dust where new stars are born, reveal the intricate dance of gravity and radiation that shapes the universe. Yet even these iconic structures, first made famous by the Hubble Space Telescope, hold secrets that Webb is only beginning to unravel. The pillars are not static monuments but dynamic ecosystems, where stars are born, evolve and die in cycles that span millions of years. Observation. Webb's infrared vision has penetrated the dusty veils of the pillars, revealing the birth cries of young stars hidden within. These protostars, still in the process of formation, emit jets of plasma that carve through the surrounding gas, sculpting it into intricate patterns. Yet the energy output of these jets exceeds the predictions of current models, suggesting that the process of star formation is far more complex than we thought. If our understanding of star birth is incomplete, it could have far-reaching implications for our theories of galactic evolution and the origin of life itself. The uninvited guest, it seems, is not just a single discovery or anomaly. It is a cascade of revelations that challenge the very foundations of our understanding. Webb is not merely expanding the universe we see, it is rewriting the rules by which we see it. As we stare into the abyss stares back, revealing not just new wonders but new mysteries that force us to question who we are and where we came from. The James Webb Space Telescope is not just a telescope, it is a portal to a universe that is both familiar and profoundly alien, a universe that demands we rethink everything. Part 2. Dark Stars Rising. What if the first stars in the universe weren't born from light, but from darkness? Webb's observations of ancient galaxies have led to a startling hypothesis: the existence of dark stars. These theoretical objects, fueled not by nuclear fusion, but by the annihilation of dark matter, were once thought to be mere ghosts of the early universe. But now they might be real. The concept of dark stars has been floating in theoretical astrophysics for decades, but it wasn't until the James Webb Space Telescope, JWST, began peering into the depths of the cosmos that scientists started to consider them as more than just mathematical curiosities. With its infrared capabilities, Webb can see through the dust and gas that obscure the universe's earliest moments, revealing structures that date back to just a few 100 million years after the Big Bang. These structures, often shrouded in mystery, could hold the key to understanding the enigmatic nature of dark matter and its role in the formation of the first stars. Interpretation: dark stars, if they exist, would rewrite the history of stellar evolution. They would suggest that the earliest structures in the cosmos were ignited not by the light of fusion, but by the unseen hand of dark matter, a substance that makes up 85% of the universe's mass, yet remains invisible to us. This would challenge Not only our understanding of how galaxies form, but also the origin of black holes and the very fabric of space-time. For instance, dark stars could explain the puzzling presence of supermassive black holes in the early universe, which seem to have grown too large, too quickly for traditional models to account for. These black holes, weighing in at billions of solar masses, are thought to have formed from the collapse of massive stars. But if those stars were dark stars, their unique physics could accelerate this process, providing a missing link in the evolution of cosmic structures. The rapid growth of these black holes could also explain the intense quasar activity observed in the young universe, where distant galaxies shine with the light of billions of suns. Dark stars, if confirmed, would also force us to rethink the role of dark matter in the universe. Currently, dark matter is understood as a passive scaffold, shaping galaxies through gravity alone. But if it can power stars, then it becomes an active participant in the cosmos, driving energy and light into the void. This would mean that the universe's first light, the moment when the cosmos transitioned from darkness to illumination, may have been fueled not by hydrogen and helium, but by the annihilation of dark matter particles. Such a process would produce a unique signature. 1. That scientists are now racing to detect with instruments like Webb and the upcoming Euclid telescope. These observatories could reveal not just the existence of dark stars, but the nature of dark matter itself, a mystery that has eluded physicists for nearly a century. The annihilation of dark matter particles could produce gamma rays, neutrinos, and other exotic particles, offering a tantalizing glimpse into the hidden majority of the universe. Imagine a universe where the building blocks of reality are not the familiar atoms and molecules, but something far more elusive. Dark matter, which we can only detect through its gravitational effects, may not just shape galaxies, it may ignite them. If this is true, then the universe is far stranger and more complex than we ever imagined. The idea of dark stars challenges the very foundations of cosmology, but it also offers a tantalizing possibility. That the unseen majority of the universe is not just a silent observer, but a catalyst for creation. In this new framework, dark matter is not a cosmic enigma but a creative force, responsible for the birth of the first stars and, by extension, the first galaxies. These galaxies, in turn, would have formed earlier and grown more rapidly, altering the timeline of cosmic history. To understand the impact of dark stars, consider the timeline of the universe. Within the first few 100 million years after the Big Bang, the cosmos was a dark and formless expanse, filled with hydrogen, helium, and dark matter. Traditional models suggest that the first stars, known as population 3 stars, formed from the collapse of massive clouds of hydrogen and helium. These stars were enormous, up to 1,000 times the mass of our Sun, and burned hot and fast, living for just a few million years before exploding as supernovae. Their short lives seeded the universe with heavier elements, paving the way for the formation of galaxies and, eventually, planets like Earth. But if dark stars existed, this timeline would shift. Dark stars, powered by dark matter annihilation, could have formed earlier and lived longer, altering the course of cosmic evolution. Their slower burn would have produced a steadier output of energy, potentially delaying the onset of the cosmic dawn, the era when the first stars and galaxies lit up the universe. The search for dark stars is not just a theoretical exercise. It has real-world consequences for astrophysics and particle physics. If dark stars are real, they could explain several mysteries in cosmology, such as the missing satellite problem, where simulations predict far more dwarf galaxies orbiting the Milky Way than are observed. Dark stars could also shed light on the nature of dark matter itself. For example, if dark matter is composed of weakly interacting massive particles, WIMPs, their annihilation in the cores of dark stars would produce gamma rays and other high-energy particles. Detecting these signals could confirm not only the existence of dark stars, but also the identity of dark matter. Such observations could revolutionize our understanding of the universe's hidden architecture, revealing the interplay between dark matter and ordinary matter in unprecedented detail. The hunt for dark stars is already underway. In 2023, a team of astronomers using Webb identified several candidate objects in distant galaxies that appear too massive and too cool to be ordinary stars. These objects, if confirmed, could be the first observed dark stars. Meanwhile, ground-based observatories like the Large Hadron Collider, LHC, are searching for signs of dark matter. Annihilation, which could provide indirect evidence for dark stars. The stakes are high. Confirming the existence of dark stars would not only rewrite the history of the universe, but also open new avenues for understanding the fundamental forces of nature. The discovery of dark stars could pave the way for breakthroughs in particle physics, gravitational theory, and even the search for extraterrestrial life, as the conditions within dark stars might. Support novel forms of chemistry and biology. In the grand tapestry of the cosmos, dark stars represent a potential revolution. They challenge our understanding of how stars form, how galaxies evolve, and how the universe came to be. But they also offer a glimpse into the unseen majority of the universe, the dark matter that shapes everything yet remains hidden from view. If dark stars are real, they are more than just celestial objects. They are beacons of a deeper reality, illuminating the dark heart of the cosmos and revealing the true nature of the universe we call home. The search continues, but the possibilities are endless. The universe, it seems, is full of surprises, and dark stars may be one of its greatest secrets. As we peer deeper into the cosmos, the story of dark stars may redefine our place in the universe, connecting us to a hidden world that has shaped the very fabric of existence. Part 3. The Water World. While Webb was peering into the depths of the cosmos, it also turned its gaze towards something much closer, a super-Earth named GJ 1214b, orbiting a red dwarf star just 40 light-years away. This planet, roughly 2.7 times the size of Earth, had long been a subject of intrigue for astronomers. Its proximity to its star meant it was initially dismissed as too hot for life, with surface temperatures estimated to reach as high as 230 T-degree, 440 C-degree. However, recent temperature mappings using advanced infrared imaging revealed something astonishing. Regions of this planet that are surprisingly temperate, hovering around 120 degrees, 248 degrees in some areas. This discovery reopened the debate about its habitability and sparked a new wave of scientific curiosity. GJ 1214b's days are perpetually locked in a fiery embrace with its star, completing an orbit every 38 hours. Despite this, the planet's thick atmosphere acts as a global heat distributor, allowing cooler zones to persist. But the real shock came when Webb detected water vapor, methane, and a heavy atmosphere unlike anything expected. The atmosphere of GJ 1214b is estimated to be over 100 times denser than Earth's, composed primarily of hydrogen and helium, with significant traces of water vapor and methane. The presence of water vapor was particularly unexpected. as it suggested the planet might, have retained a substantial amount of water despite its intense stellar radiation. Methane, on the other hand, is a gas that often hints at biological processes on Earth, though it can also be produced through geological means. The detection of these compounds was made possible by Webb's near-infrared spectrograph, NIR spec, which can discern the chemical fingerprints of distant worlds with unprecedented precision. Observation: GJ 1214b may be. Entirely covered in a vast ocean, a true water world, the presence of methane and water vapor together is often a strong indicator of life. The possibility of a global ocean is supported by the planet's low density, which suggests it is composed of about 50% water by mass. This would make it one of the most water-rich worlds ever discovered, dwarfing Earth's own 0.02% water composition. But there's more. Webb also detected signs of dimethyl sulfide, a compound on Earth produced only by living organisms like phytoplankton. This raises a tantalizing question. Could we be looking at the first real evidence of alien biochemistry? The ocean of GJ 1214b, if it exists, would be unlike anything on Earth. A roiling, steamy expanse beneath a reddish sky, illuminated by a star that appears 100 times brighter than our sun does from Earth. The detection of dimethyl sulfide is particularly intriguing because it is a byproduct of biological processes on Earth, specifically linked to marine life. Phytoplankton, tiny plant-like organisms that float in the ocean, produce dimethyl sulfide as part of their metabolic activity. This compound then escapes into the atmosphere, where it plays a key role in cloud formation and climate regulation. If a similar process is occurring on GJ 1214b, it could suggest the presence of a complex biosphere hidden beneath its thick, hazy atmosphere. The clouds of GJ 1214b, tinted orange and brown by the dimethyl sulfide and other atmospheric compounds, could be teeming with microscopic life forms suspended in the skies, adapted to survive in the planet's unique environment. Speculation. If GJ 1214b harbours life, it would mean that the conditions for its emergence are far more common than we thought. A world that was considered dead just last year may now be teeming. With possibilities, the implications of this discovery are staggering. If life can exist on a planet so close to its star, subjected to such intense radiation, it challenges our understanding of habitability. It also raises questions about the potential for life on other super-Earths, a class of exoplanets that are increasingly being identified in the cosmos. Super-Earths, which are more massive than Earth but smaller than ice giants like Neptune, are now thought to be the most common type of exoplanet in the Milky Way. Of the more than 5,000 confirmed exoplanets, roughly 30% fall into this category, making GJ 1214b a critical case study for understanding their potential habitability. Astronomers estimate that there are billions of exoplanets in the Milky Way galaxy alone, and a significant fraction of these are super-Earths. If GJ 1214b proves to be habitable, it could mean that life is not a rare exception, but a common feature of the universe. The search for life beyond Earth has long been focused on planets within the habitable zone, where temperatures are thought to be suitable for liquid water. However, GJ 1214b's example suggests that life might find ways to thrive in environments we once deemed inhospitable. Its atmosphere, for instance, is so dense that it creates a greenhouse effect far more powerful than Earth's, trapping heat and allowing liquid water to persist despite the planet's scorching proximity to its star. The discovery of potential life on GJ 1214b would also have profound implications for our understanding of biochemistry. Life on Earth is based on carbon, hydrogen, oxygen, and nitrogen, with water serving as the universal solvent. However, the conditions on GJ 1214b, with its dense, hydrogen-rich atmosphere and extreme temperatures, could support entirely. Different forms of biochemistry. This opens the door to the possibility of alien life forms that are fundamentally different from anything we have ever imagined. For example, organisms on GJ 1214b might use hydrogen sulfide or ammonia as solvents instead of water, or they might rely on silicon-based compounds rather than carbon-based ones. Such life forms could metabolize energy in ways that are completely foreign to Earth-based biology. And if life can thrive there, how many other worlds in the cosmos are waiting to be discovered? The James Webb Space Telescope, with its unparalleled sensitivity and resolution, is poised to answer this question. In the coming years, it will continue to scrutinize exoplanets like GJ 1214b, searching for telltale signs of habitability and life. Each new observation will bring us one step closer to understanding our place in the universe and whether we are truly alone in the vast expanse of the cosmos. Webb's infrared capabilities allow it to peer through the dust and gas that obscure many exoplanets, revealing their atmospheric compositions and surface conditions in stunning detail. Its findings could redefine our notion of habitable zones, expanding the search for life to worlds once considered uninhabitable. As Webb's gaze shifts from one world to the next, it paints a picture of a universe brimming with possibilities. GJ 1214b, with its tantalizing hints of water and life, is just the beginning. With every new discovery, we are rewriting the story of our cosmic origins and expanding the boundaries of what it means to be alive. The next decade of exoplanet exploration promises to be one of the most transformative periods in human history, as we uncover the secrets of distant worlds and perhaps the first definitive evidence of extraterrestrial life. Every time Webb trains its mirrors on a new target, it brings us closer to answering the age-old question: are we alone in the universe? The answer, it seems, may be hidden in the depths of a water world, shimmering beneath the light of a distant star. Part 4. Cosmic Smoke. What if the smoke from a matchstick shared something in common with galaxies 12 billion light-years away? Webb recently detected polycyclic aromatic hydrocarbons, compounds typically associated with smoke, near the very edge of the observable universe. These molecules, found in tobacco smoke, car exhaust, and burned organic matter on Earth, are considered prebiotic, crucial for forming DNA, proteins, and cells. Imagine the faint, flickering glow of a matchstick in a dark room, its tendrils of smoke curling upward. Now scale that image to the cosmos, where similar compounds drift through the void, illuminated not by a match, but by the light of distant galaxies. These PAHs are not mere specks of dust. They are intricate structures of carbon and hydrogen, often arranged in hexagonal rings that resemble the geometry of a honeycomb. Their ubiquity is astonishing. They account for up to 15% of the total carbon in the Milky Way, making them one of the most abundant organic molecules in the universe. These polycyclic aromatic hydrocarbons, or PAHs, are not just idle components of interstellar dust. They are active participants in the chemistry of the cosmos, capable of absorbing ultraviolet radiation and re-emitting it in the infrared spectrum, making them detectable by instruments like Webb. Their presence in the cosmos is not a new discovery. They have been observed in the Milky Way and other nearby galaxies for decades. However, Webb's detection of PAHs in galaxies so distant and ancient galaxies that formed just 750 million years after the Big Bang, is a revelation. These are not the mature, well-ordered galaxies of the present-day universe, but chaotic, turbulent systems still in the process of formation. In these primordial galaxies, stars are born at rates hundreds of times faster than in the Milky Way today, their intense ultraviolet radiation bathing the interstellar medium and triggering complex chemical reactions. Interpretation. The presence of these compounds so far from us suggests that the building blocks of life were already drifting through the cosmos just 750 million years after the Big Bang. If the ingredients for life were present so early, what was stopping it from emerging elsewhere long before it did on Earth? This question is not merely academic. The Earth itself did not form until approximately 9 billion years after the Big Bang, and life did not emerge here until at least another billion years after that. Yet the universe was already seeded with the chemical precursors for life when it was still in its infancy. Were these ingredients simply waiting for the right conditions to spark into something more complex? Or were there earlier, unimaginable forms of life that emerged and vanished, leaving no trace in the cosmic record? This discovery raises profound questions about the origins of life. Are we the product of a cosmic recipe that has been repeated countless times across the universe? Or are we a rare anomaly in an otherwise silent cosmos? Astronomers estimate that there are roughly 2 trillion galaxies in the observable universe, each containing, on average, hundreds of billions of stars. If even a fraction of these stars host planets with conditions similar to Earth's, the potential for life elsewhere becomes statistically significant. Yet, for all our searching, we have found no definitive evidence of extraterrestrial life, a paradox known as the Fermi problem. The silence of the cosmos remains one of the greatest mysteries in astrobiology. Perhaps life is rare, or perhaps it exists in forms so alien to our understanding that we fail to recognize it. The detection of PAHs in these distant galaxies is not just a curiosity. It has implications for our understanding of how life might arise elsewhere. These molecules are not life itself, but the raw materials from which life could potentially emerge. On Earth, PAHs are thought to have played a critical role in the formation of the first organic compounds in the primordial soup. They are stable, carbon-rich, and capable of forming complex structures, making them ideal candidates for the chemical scaffolding upon which life could build itself. Their presence in the early universe suggests that the conditions for life may have been widespread long before the Earth even existed. In fact, laboratory experiments have shown that PAHs can catalyze the formation of amino acids and nucleobases, the building blocks of proteins and DNA, when exposed to conditions mimicking those of the early Earth. Observation. The galaxies where Webb detected PAHs are not static, unchanging objects. They are dynamic, evolving systems shaped by the forces of gravity, star formation, and supernovae. In these galaxies, stars are born, live out their lives, and die in spectacular explosions, spreading their contents into the interstellar medium. This cycle of birth, death, and rebirth enriches the galaxy with heavier elements, including the carbon, oxygen, and nitrogen that make up PAHs. Over time, these elements coalesce into new stars and planets, potentially seeding the universe with the ingredients for life. In one such distant galaxy, Webb observed a supernova remnant glowing with the infrared signature of PAHs, evidence that these molecules are forged in the crucibles of stellar explosions and dispersed across cosmic distances. speculation if life did emerge elsewhere in the universe. It may have followed a similar path to that on Earth, beginning with simple organic compounds like PAHs and gradually evolving into more complex forms. However, it is also possible that life elsewhere took a completely different path, one that we cannot yet imagine. The diversity of life on Earth is a testament to the adaptability of biological systems, and the universe is far more diverse than our single planet. For instance, some theoreticians have proposed that life could arise in the dense atmospheres of gas giant planets, where complex organic molecules could form and interact in ways entirely unlike anything found on Earth. The search for extraterrestrial life is not just a search for alien organisms, but a search for entirely new forms of biology shaped by environments and conditions we have yet to discover. The quest to understand the role of PAHs in the cosmos is far from over. Future observations with Webb and other advanced telescopes will probe even deeper into the universe, searching for these molecules in galaxies that formed just a few 100 million years after the Big Bang. By studying the distribution and abundance of PAHs across cosmic time, astronomers hope to piece together the story of how the universe evolved from a primordial soup of simple atoms into a cosmic ecosystem teeming with the potential for life. Each new detection of PAHs adds another chapter to this story, bringing us closer to understanding whether we are alone in the universe or part of a vast, interconnected web of life that stretches across the stars. Status. Update. As of now, Webb's observations have revealed ancient galaxies that defy our models of formation, hints of dark stars powered by dark matter annihilation, and the potential building blocks of life near the edge of the observable universe. Yet, for all we've learned, the mysteries have only deepened. The universe seems to be hiding more than it reveals. Each new discovery brings with it a cascade of questions, challenging our assumptions and forcing us to reevaluate our place in the cosmos. The detection of PAHs in distant galaxies is just one piece of this puzzle, a tantalizing clue that the building blocks of life may be universal. But the question remains, are we alone in the universe, or are there other beings out there, looking up at the stars and wondering the same thing? As Webb continues to peer into the depths of space, the answers to these questions may finally come into focus, illuminating not just the cosmos, but our place within it. Part 5. The Impossible Black Holes. Webb's deep field images have uncovered another unsettling discovery: galaxies with supermassive black holes, some 1,000 times larger than the one at the center of our Milky Way, forming less than 100 million years after the Big Bang. These behemoths are staggering in scale, with masses exceeding 1 billion times that of our Sun, yet they exist in a universe barely 7% of its current age. According to our current understanding of physics, this shouldn't be possible. It takes billions of years for such black holes to grow as they slowly devour stars and gas, accumulating mass over eons. Yet there they are, fully formed, defying explanation. Their presence challenges not only our timelines of cosmic evolution, but also the very laws that govern the growth of these enigmatic objects. Astronomers have long believed that black holes grow gradually, feeding on the material around them in a slow, steady process. But these early giants seem to have bypassed this slow growth, emerging fully formed in a cosmic blink of an eye. In the heart of these ancient galaxies, supermassive black holes dominate their surroundings, their gravitational pull so immense that they warp space-time itself. These galaxies are like miniature versions of the Milky Way, but denser, brighter, and more evolved than they have any right to be. Their stars are packed tightly. Together, glowing fiercely with the light of youth while their black holes loom at the center, silent and inscrutable. Imagine a galaxy like a cosmic metropolis, its stars like skyscrapers stretching toward the heavens. Now compress that city into a fraction of its size, intensify its light and place a monstrous black hole at its core. That is what these early galaxies look like. Cosmic cities in fast forward, their development accelerated beyond. Comprehension. Some scientists have dubbed this a cosmic crisis, a fundamental breakdown in our theories of cosmology. It is as if we have stumbled upon a universe that has aged too quickly, its structures too advanced for the time in which they exist. Observation. The galaxies housing these impossible black holes are not merely anomalies. They are harbingers of a deeper mystery. Their formation seems to contradict the established models of galaxy. Evolution. In the early universe, the first stars were massive and short-lived, exploding as supernovae and seeding the cosmos with heavy elements. However, the rapid assembly of supermassive black holes suggests that something else is at play. Perhaps the first black holes were not born from the collapse of single stars, but from more exotic processes, such as the direct collapse of colossal gas clouds or the merging of primordial black holes formed. In the Big Bang's aftermath, these primordial gas clouds, known as direct collapse black holes, could have been hundreds of thousands of times more massive than the Sun, collapsing under their own gravity to form black holes almost instantly. These primordial galaxies are not isolated cases. Webb's observations have revealed dozens of these enigmatic objects, scattered across the early universe like cosmic breadcrumbs. Each one is a puzzle piece, hinting at a larger, hidden picture. Their black holes are not just massive but hyperactive, consuming matter at rates that defy conventional wisdom. The accretion disks surrounding these black holes glow with intense radiation, outshining entire galaxies. This frenzied activity suggests that the early universe was a more chaotic and dynamic place than we ever imagined, a cauldron of creation and destruction. Picture these accretion disks as swirling. Maelstroms of gas and dust heated to temperatures that emit blazing light across the electromagnetic spectrum. They are cosmic lighthouses, signaling the presence of these impossible black holes from billions of light years away. Interpretation. The existence of these impossible black holes forces us to rethink the fundamental laws that govern the cosmos. Or if our current models cannot explain their presence, then perhaps those models are incomplete. Some researchers have proposed that the early universe may have been denser than we thought, allowing black holes to grow more rapidly. Others suggest that dark matter, the mysterious substance that permeates the cosmos, may have played a role in their formation. Dark matter, which accounts for roughly 85% of the matter in the universe, could have acted as a gravitational scaffold, helping to concentrate material and accelerate the growth of these. Black holes. Still, these explanations feel insufficient, like pieces of a puzzle that don't quite fit. Speculation. To explain these impossible black holes, some theorists have proposed wildly exotic scenarios. One idea involves the rapid collapse of primordial gas clouds, which could have formed directly into supermassive black holes without the need for intermediate steps. Another suggestion is the merging of multiple smaller black holes in the early universe. a process that would require unprecedented rates of collision and coalescence. But even these explanations strain the limits of what we consider possible. They push the boundaries of physics, forcing us to confront the unknown and question the very foundations of our understanding. Some have even floated the idea of seed black holes, tiny primordial black holes formed in the Big Bang's aftermath, which grew rapidly by consuming vast amounts of gas and merging with other black holes. Imagine the early universe, a place of fire and fury, where matter and energy intertwine in a dance of creation. In this primordial chaos, black holes form and grow at rates that seem impossible by today's standards. They are the titans of the cosmos, shaping the structures around them with their immense gravitational pull. Their existence challenges us, beckoning us to explore the unknown and rewrite the rules of the universe. As we stare into the abyss of these impossible black holes, we cannot help but wonder, what other mysteries lie hidden in the depths of the cosmos, waiting to be discovered? Perhaps these black holes are not just anomalies, but signposts pointing toward a new understanding of the universe, one where the laws of physics are more flexible, more dynamic, and more profound than we ever imagined. Part 6. Echoes of Another Universe. One of the most disturbing possibilities emerging from Webb's data is the idea that our universe may not have had a single beginning. Buried deep in the gravitational lensing around ancient galaxy clusters, scientists have noticed anomalies, echoes of expansion that don't align with the standard Big Bang model. These discrepancies, though subtle, have sparked intense debate among cosmologists. The gravitational lensing effect, where massive objects, like galaxy clusters, bend and magnify the light of objects behind them, acts as a natural telescope, allowing astronomers to peer deeper into the cosmos than ever before. In these magnified images, faint distortions and unexplained patterns have emerged, hinting at a universe that may not have begun with the singular event we call the Big Bang. The James Webb Space Telescope, with its infrared capabilities, has captured these anomalies with unprecedented clarity. Launched in 2021, Webb's 6.5-meter gold-coated mirror and advanced sensors have enabled it to detect light from the earliest stars and galaxies, some of which formed just 100 million years after the Big Bang. However, the data it has returned suggests that certain regions of the universe are expanding at rates that defy the predictions of the standard cosmological model. These deviations are not small. Some regions appear to be expanding up to 9% faster than the Hubble constant would predict. This has led researchers to question whether the Big Bang was truly the singular origin of our universe or just the latest chapter in a much older story. Hypothesis: the theory of a cyclical universe where the cosmos is born, dies and is reborn like a cosmic phoenix, is gaining traction. If Webb's readings are accurate, the rate of expansion in certain regions doesn't match the Hubble constant. We may be witnessing remnants of a previous cosmic cycle. This hypothesis, known as the ekpyrotic universe model, proposes that the universe goes through repeated cycles of expansion and contraction, driven by the collision of higher dimensional objects called branes. These collisions, according to the theory, could create the conditions for a new Big Bang, resetting the cosmos and giving rise to a new cycle of existence. Observation: the anomalies detected by Webb are not isolated incidents. They appear in multiple regions of the universe, suggesting a pattern rather than random fluctuations. For instance, in the galaxy cluster Abell 2744, nicknamed Pandora's cluster, the gravitational lensing reveals a complex web of dark matter that doesn't align with the distribution of visible matter. This discrepancy has led some scientists to propose that the cluster may contain remnants of a previous cosmic cycle, where the dark matter distribution was shaped by events that predate the Big Bang. Interpretation: if these anomalies are indeed evidence of a cyclical universe, it would mean that our current cosmos is just one iteration in an endless sequence. The implications of this are staggering. It would redefine our understanding of time, space, and the very nature of existence. It would also raise questions about the fate of information and energy across cosmic cycles. Did the previous universe leave behind traces of its own history, embedded in the fabric of space-time? And if so, could these traces influence the evolution of our own universe? Speculation. Some researchers have proposed that the remnants of a previous universe could manifest as subtle fluctuations in the cosmic microwave background, CMB radiation. This faint afterglow of the Big Bang, discovered in 1964 by Arno Penzias and Robert Wilson, provides a snapshot of the universe when it was just 380,000 years old. However, tiny irregularities in the CMB, detected by satellites like the Planck Observatory, could be interpreted as echoes of events that occurred before the Big Bang. These pre-Big Bang signals, if confirmed, would support the cyclical universe hypothesis and challenge the prevailing view of cosmic origins. This raises chilling questions. Are we living in just one version of many? Are there traces of a forgotten universe lingering beneath our own? And if so, what did it leave behind? The search for answers has led to ambitious new projects, such as the Euclid mission, scheduled to launch in 2023. Euclid, a European Space Agency telescope, will map the distribution of dark matter and dark energy across the universe with unprecedented precision, by comparing Euclid's data with Webb's observations. Scientists hope to uncover whether the anomalies are mere statistical outliers or the first tangible evidence of a universe reborn. In the quiet corners of the cosmos, where ancient light bends and twists around unimaginable masses, the echoes of another universe may be whispering their secrets. The quest to decipher these whispers is not just a scientific endeavor. It is a journey into the very heart of existence. What we learn from these echoes could redefine our place in the cosmos and reveal that our universe is not a solitary creation, but a single note in an eternal symphony of birth, death, and rebirth. Part 7. The Ring of Galaxies. The camera pans across a star field, then zooms in on a structure so enormous it seems impossible, a perfect ring of galaxies glittering like a cosmic crown. This isn't a trick of perspective or a gravitational lens, it's a real formation. A circular chain of galaxies stretching over 1.3 billion light-years. To put this into perspective, light, travelling at roughly 300,000 kilometers per second, takes 1.3 billion years to traverse this structure. The sheer scale of it is staggering. Our Milky Way galaxy, vast as it seems, would fit into this ring over 1,000 times. The discovery left astrophysicists in stunned silence, as it defies everything we understand about gravity, structure formation, and the laws of entropy. When the first images of the ring arrived, researchers double-checked the data, suspecting instrument error or an optical illusion. Teams at the European Space Agency and NASA independently verified the findings using data from the Planck satellite and the Hubble Space Telescope. But the observations held firm. Deep field scans revealed that the galaxies in the ring were not just aligned by chance. They were gravitationally bound, moving in a synchronized dance that seemed to defy the accepted laws of cosmic evolution. The ring's existence was a cosmic enigma, a puzzle that challenged the very foundations of astrophysics. Interpretation. Some theorists are now exploring whether this ring could be evidence of topological defects in space-time, cosmic bruises left behind when the universe cooled too quickly after the Big Bang. Imagine the universe in its infancy, a seething cauldron of energy and matter expanding at an unfathomable rate. As it cooled, imperfections may have formed, like cracks in cooling lava. These structures have only ever existed in simulations and string theory papers until now. The camera zooms in on a simulation of the early universe, a roiling chaos of energy and matter. As the universe expands and cools, tiny fluctuations in density give rise to the first galaxies, like stars on a cosmic scale. But in this simulation, something goes awry. A region of space-time cools too quickly, forming a topological defect, a crack in the fabric of reality. The ring of galaxies could be one of these cracks. A scar from the violent and chaotic birth of the cosmos. If this interpretation is correct, it would rewrite our understanding of the universe's earliest moments. The Big Bang is often visualized as a smooth, uniform expansion, but the existence of topological defects suggests a far more turbulent beginning. These defects, if proven, could explain anomalies in the cosmic microwave background radiation, the faint afterglow of the Big Bang that have puzzled scientists for decades. Imagine the cosmic microwave background not as a smooth glow, but as a surface rippled with tiny fluctuations, echoes of the universe's chaotic birth. On such anomaly is the cold spot, a region in the cosmic microwave background that is significantly colder than its surroundings. Some researchers have proposed that this could be the result of a topological defect, a scar in space-time that affects the temperature of the universe's earliest light. If true, this would provide further evidence for the existence of these defects and their role in shaping the cosmos. But the implications don't end there. If topological defects exist, they could profoundly affect our understanding of gravity itself. Einstein's general theory of relativity describes gravity as the curvature of space-time caused by mass and energy. But what if space-time itself is not uniform? What? If these defects create localized distortions, regions where gravity behaves in unexpected ways, such possibilities could explain the mysterious acceleration of the universe's expansion, currently attributed to dark energy, a phenomenon we can observe but cannot yet explain. The camera now shifts to a montage of scientists at work, supercomputers humming as they simulate cosmic structures, whiteboards covered in equations and heated debates in conference rooms. The ring of galaxies has sparked a frenzy of research, drawing together experts from cosmology, particle physics and theoretical mathematics. Teams are scouring the sky for more evidence of topological defects, using the latest telescopes and algorithms to hunt for patterns in the cosmic web. At the Max Planck Institute for Astrophysics, a team of researchers is developing new algorithms to analyze data from the upcoming Euclid mission, a space telescope designed to map the dark universe. Meanwhile, at the University of California, Berkeley, physicists are using the Advanced Laser Interferometer Gravitational Wave Observatory, LIGO, to detect gravitational waves, ripples in space-time caused by massive cosmic events. If topological defects exist, they could produce unique gravitational wave signatures, offering a new way to study these enigmatic structures. Observation. In the years since the ring's discovery, several other anomalies have been detected. One team reported a cosmic filament, a thread of galaxies stretching over 4 billion light-years, far longer than any known structure. Known as the Boss Great Wall, This filament is so vast that it challenges our understanding of large-scale structure formation. Another group identified a region of space where galaxies seemed to be missing, as if something had cleared them away. This cosmic void, spanning over 1 billion light-years, is one of the largest known structures in the universe and could be evidence of a topological defect. The camera lingers on an artist's impression of a cosmic void, a vast region of emptiness surrounded by a web of galaxies. As the camera moves closer, the edges of the void begin to shimmer, hinting at the presence of a topological defect, a crack in space-time that has shaped the universe. Around it, these findings, though preliminary, suggest that the ring is not an isolated phenomenon, but part of a larger, hidden architecture in the universe. Speculation. Are there other topological defects waiting to be discovered, and what secrets do they hold? Could these defects be connected to the mysterious phenomena of dark matter and dark energy, which together make up 95% of the universe's mass-energy budget yet remain invisible to our instruments? Some researchers have even proposed that topological defects could act as gateways to other universes, portals through the fabric of space-time itself. Imagine a universe where the laws of physics are different, where time flows backward, or where the fundamental constants of nature are not constant at all. The camera lingers on a close-up of the ring, its galaxies glowing like jewels against the void. This is not just a pretty picture. It is a window into the unknown, a glimpse of a cosmos far stranger and more wondrous than we ever imagined. The search for answers continues, driven by curiosity, ambition, and the human desire to understand our place in the vast expanse of the universe. But for now, the ring of galaxies remains a mystery, a cosmic riddle that challenges everything we know about the universe. Its discovery has shaken the foundations of astrophysics, forcing us to question our most fundamental assumptions about reality. Yet it also offers a thrilling opportunity, a chance to rewrite the story of the cosmos and in doing so to redefine our place within it. As we stand on the precipice of this new frontier, we are reminded of the words of astronomer Carl Sagan. Somewhere, something incredible is waiting to be known. Part 8. The Signal. Buried in the noise of deep space radio data, an unexpected pattern has surfaced. Webb wasn't designed to listen, but even its instruments have picked up strange modulations in the electromagnetic background, pulses that repeat with eerie precision. Initially thought to be glitches, cross-checking with older Voyager and Chandra, data revealed the same frequencies coming from the same region. The signals, first detected in 2028, have persisted for nearly 5 years, their origin pinpointed to a cluster of ancient galaxies over 13 billion light-years away. The consistency of the pulses defies explanation, occurring every 18.7 seconds with variations so slight they seem deliberate. Each pulse lasts exactly 0.34 milliseconds, a duration that scientists have struggled to attribute to any known natural phenomenon. The signals are so faint that they were almost overlooked, hidden within the vast amounts of data collected by Webb and other observatories. It took a dedicated team of analysts working for over 18 months to isolate the pattern, a painstaking process that involved sifting through terabytes of cosmic noise. Observation. These signals are consistent, persistent, and aimed precisely in our direction. They are too structured to be random, yet we cannot decode them. They could be a natural phenomenon, or something far more extraordinary. The pulses are not merely noise. They exhibit complex patterns that resemble coded transmissions, with repeating sequences that defy known astrophysical processes. Each burst carries a unique signature, akin to a cosmic fingerprint, suggesting an intentional design rather than a random occurrence. The signals have been compared to the enigmatic "wow" signal detected in 1977, but unlike that brief and never-repeated event, these pulses have endured, providing a wealth of data for analysis. One of the most intriguing aspects is their frequency modulation, which shifts in a way that seems to account for the Doppler effect, as if the source is compensating for its own motion relative to Earth. The global scientific community has mobilized to study the phenomenon. Teams at the Square Kilometre Array in Australia and the Event Horizon Telescope have confirmed the signals, while researchers at CERN have attempted to simulate their behavior using quantum algorithms. Despite these efforts, the signals remain enigmatic, their source and purpose elusive. Some scientists have likened the patterns to mathematical constants, while others see echoes of prime number sequences, hinting at a level of intelligence far beyond human comprehension. The signals have even been compared to the golden ratio, with some researchers suggesting that their structure aligns with this ubiquitous mathematical constant found throughout nature and art. The sheer complexity of the patterns has led to the creation of a dedicated international task force, comprising over 300 scientists from 18 countries, all focused on unraveling the mystery. Speculation. If these signals are engineered, it would mean we are not alone. Something out there is not only aware of our existence, but may already be watching us. The implications are staggering, raising questions about the nature of intelligence in the universe and our place within it. Such a discovery would rewrite not only astronomy, but philosophy, ethics, and every facet of human thought. It would challenge our understanding of what it means to be sentient, to communicate, and to exist in a universe that is not ours alone. The signals could represent the first evidence of a Type 3 civilization on the Kardashev scale. A society capable of harnessing the energy of an entire galaxy. This would place them billions of years ahead of human technological development, making their intentions and capabilities almost incomprehensible to us. The possibility of extraterrestrial intelligence has long been the subject of speculation, but never before has evidence been so compelling. The signals, if proven to be artificial, would mark the first undeniable contact with another civilization. This raises profound questions about their intentions, their technology, and their understanding of the cosmos. Are they observers, benevolent guides, or something more inscrutable? And why now, after billions of years, have they chosen to reveal themselves to us? Some theorists have proposed that the signals might be part of a larger cosmic beacon system, designed to guide emerging civilizations like ours toward greater understanding. Others have suggested a more unsettling possibility, that the signals are a test, a means for an advanced civilization to evaluate our readiness for contact. The implications of the signals extend beyond the scientific realm. Governments worldwide have convened secretive committees to discuss the potential societal impact of first contact. The United Nations has drafted protocols for responding to extraterrestrial intelligence, though these remain classified. Meanwhile, religious institutions, philosophers, and even artists have begun to grapple with the existential questions posed by the signals. What does it mean to share the universe with another thinking species? How would their presence reshape our sense of purpose, our morality, our very identity as humans? Many religious leaders have already started to address the theological implications, with some suggesting that the signals could be a manifestation of divine will, while others view them as a challenge to traditional beliefs about humanity's uniqueness in the cosmos. The signals have also sparked a cultural phenomenon. Documentaries, films, and books have emerged, exploring the possibilities and implications of the discovery. Social media platforms are abuzz with theories and debates ranging from scientific speculation to wild conspiracy theories. Art installations inspired by the signals have been exhibited in major galleries, with one piece featuring a pulsing light display that mimics the exact rhythm of the cosmic pulses. Even music has been influenced, with composers creating symphonies based on the mathematical patterns embedded in the signals. The public fascination with the signals has reached a level not seen since the Apollo moon landings, with millions of people around the world following the latest developments with bated breath. In the scientific community, the signals have led to a renewed interest in the search for extraterrestrial intelligence, SETI. Funding for SETI projects has increased dramatically, with new observatories and research initiatives being launched around the globe. One such project, the Cosmic Echo Initiative, aims to build a network of radio telescopes specifically designed to detect and analyze signals from deep space. The initiative has already secured funding from several governments and private donors, with construction set to begin in 2035. The hope is that by expanding our ability to listen to the universe, we may uncover more signals like these, furthering our understanding of the cosmos and our place within it. However, not everyone is optimistic about the potential of the signals. Some scientists and philosophers have expressed concern about the risks of first contact. They argue that encountering an intelligence far beyond our own could be destabilizing, both socially and psychologically. What if the signals reveal truths about the universe that challenge our most deeply held beliefs? What if they expose our own limitations in ways we cannot yet comprehend? These questions have led to the establishment of a new field of study known as cosmic anthropology, which seeks to understand the potential impact of extraterrestrial contact on human society. Researchers in this field are already working to develop frameworks for how humanity might respond to such an event, drawing on insights from history, psychology, and sociology. Despite the uncertainties, the signals have undeniably reignited humanity's sense of wonder. They have reminded us that the universe is vast and full of mysteries waiting to be discovered. For many, the signals represent a call to action, a challenge to push the boundaries of our knowledge and exploration. Space agencies around the world have announced new missions inspired by the discovery, including plans to send probes to the outer reaches of the solar system and beyond. Private companies are also getting involved, with several announcing ambitious projects to develop interstellar travel technology. The dream of reaching the stars, once the stuff of science fiction, now seems closer than ever. Status. Update. Webb's discoveries have shaken the foundations of modern physics. From dark stars and impossible black holes to cyclical universes and topological defects, the telescope is revealing a cosmos far stranger than we ever imagined. Yet, for all its revelations, the mysteries only seem to grow. The signals, in particular, represent a turning point in our understanding of the universe. They challenge us to look beyond our own world, to consider the possibility of companionship in the vast expanse of space and time. As Webb continues to peer deeper into the cosmos, the signals remain a constant reminder of the unknown. They are a beacon, a call from the edge of reality, urging us to push the boundaries of our knowledge and imagination. Whether they are the voice of another civilization or the echo of some unknown cosmic process, they have forever changed our perspective. We are no longer alone in the universe, not in spirit, and perhaps not in fact. The signals are a testament to the endless possibilities that lie beyond our world, waiting to be discovered, understood, and embraced. Part 9. The Unseen Mass. As Webb continues to peer further into the cosmos, it has begun to detect structures that don't even emit light at all. Gravitational anomalies hidden within what should be empty voids. Imagine a region of space with no stars, no galaxies, no detectable matter. Yet something there is bending the light around it, warping the fabric of space-time in ways that defy our current understanding of astrophysics. These anomalies often appearing as subtle. Distortions in the cosmic microwave background or slight shifts in the trajectories of distant stars hint at the presence of unseen masses that exert a gravitational pull despite their invisibility. Astronomers have identified at least 36 such regions within the observable universe, each one a mystery that challenges the boundaries of modern science. Observation. These invisible mass islands aren't accounted for by dark matter simulations. Dark matter, which constitutes approximately 27% of the universe, is believed to interact with ordinary matter primarily through gravity. However, the gravitational effects observed in these anomalous regions exceed the predicted influence of dark matter by factors of 5 or more. Some physicists suspect the existence of entire regions of alternate physics, zones where the laws that govern our universe simply don't apply. These regions might be remnants of the early universe where conditions were so extreme that they imprinted permanent deviations in the fundamental forces. Alternatively, they could represent areas where the fabric of space-time itself has been altered by unknown cosmic events, creating pockets of reality that operate under different rules. Speculation. If this is true, we're not just seeing through space. We're peering into other versions of reality embedded inside our own, like pockets of a cosmic multiverse tangled in gravitational knots. What else could exist in those places where our rules no longer hold? Some theories suggest that these regions could harbor entirely new forms of matter or energy, undetectable by our current instruments, but profoundly influencing the universe on scales we are only beginning to comprehend. Others propose that these anomalies might be gateways to other dimensions, where the constants of physics, such as the speed of light or the strength of gravity, take on entirely different values. If such dimensions exist, they could host parallel universes with their own unique histories, life forms, and even civilizations, all existing alongside our own, but forever separated by the boundaries of physics. The implications of these gravitational anomalies extend far beyond theoretical physics. If these regions represent pockets of alternate reality, they could revolutionize our understanding of the universe's origins and evolution. For example, the Big Bang theory, which describes the birth of our universe as a singular event, might need to be re-evaluated in light of these discoveries. Perhaps our universe is just one of many, each born from a different cosmic event and governed by its own unique set of laws. This idea, known as the multiverse hypothesis, has been debated for decades, but the calm detection of these anomalous regions provides the first tangible evidence that such a structure might exist. Observation. The search for these anomalies has also led to unexpected advancements in technology and methodology. To detect these subtle gravitational distortions, astronomers have developed new instruments capable of measuring changes in space-time with unprecedented precision. These tools, such as advanced interferometers and next-generation telescopes, have not only expanded our ability to observe the universe, but have also opened new avenues for research in fields like quantum mechanics and particle physics. For instance, the study of these anomalies has led to breakthroughs in our understanding of gravitational waves, ripples in space-time caused by massive cosmic events like black hole mergers. By studying how these waves interact with the anomalous regions, scientists hope to uncover new insights into the nature of gravity itself. Speculation. As we continue to explore these unseen masses, we may uncover not just new physics, but new possibilities for existence itself. If these regions are indeed gateways to other dimensions or realities, they could hold the key to understanding the ultimate questions of existence. Why are we here? What lies beyond our universe? And are we alone in the cosmos? The search for life beyond Earth has long been confined to our own universe, but the discovery of these anomalies raises the tantalizing possibility that life could exist in forms and environments we have never considered. Perhaps in these alternate realities, the conditions for life are entirely different, shaped by laws of physics that we cannot yet imagine. The journey to unravel the mysteries of these gravitational anomalies is only just beginning. With each new observation, we edge closer to a deeper understanding of the cosmos and our place within it. Whether these regions represent the edges of our universe or the beginnings of entirely new ones, their study promises to redefine the boundaries of human knowledge and imagination. As Webb and future telescopes continue to probe the depths of space, the unseen masses will gradually come into focus, revealing a universe far stranger and more wondrous than we ever dared to dream. Part 10. The Observer Effect. Webb may not just be exposing the secrets of the cosmos, it might be reshaping them as we speak. Known as the cosmic observer effect, this theory suggests that our very active observation on such a massive scale might influence the quantum states of distant particles, causing effects we don't yet understand. The James Webb Space Telescope, with its 6.5-meter gold-coated mirror and sensitivity to infrared light, is not just a passive observer, but a tool that could potentially alter the very fabric of reality it examines. Its ability to peer into the distant past, up to 13.6 billion years ago, means it is observing light that has travelled for eons, interacting with countless particles along the way. The sheer scale of Webb's observations, covering galaxies, stars, and exoplanets across vast stretches of space and time, amplifies the potential for the observer effect to manifest in unprecedented ways. The cosmic observer effect is not merely a philosophical curiosity. It has roots in quantum mechanics, where the act of measurement can fundamentally alter the system being observed. This phenomenon, known as the quantum measurement problem, has been demonstrated in laboratories on Earth. For example, the double-slit experiment shows that particles like electrons behave differently depending on whether they are being observed when unobserved. They exhibit wave-like behavior, passing through two slits simultaneously. However, when measured, they collapse into particle-like behavior, passing through only one slit. If such effects can occur in controlled experiments, what might happen when we scale up to the cosmos, where Webb is observing trillions of particles across unfathomable distances? Interpretation. Some scientists are calling this the quantum entanglement of perception. Our gaze isn't passive, it's active, intrusive. If reality is this sensitive to being watched, then we must ask, What happens when we stare too long into the void and it begins to stare back? This question is not just metaphorical. The concept of quantum entanglement, where particles become linked and instantaneously affect each other regardless of distance, suggests that our observations could have far-reaching consequences. For instance, if Webb observes a galaxy 10 billion light-years away, the quantum states of particles in that galaxy could become entangled with particles in our own, potentially altering their behavior in ways we cannot predict. This raises profound questions about the nature of observation and the limits of human understanding. Are we merely observers of the cosmos, or are we active participants in its unfolding story? The idea that our observations could influence the universe challenges the very foundations of scientific inquiry. It suggests that our quest to understand the cosmos is not a one-way street, but a dynamic interplay between observer and observed. This interplay could have implications for our understanding of time, space, and even consciousness. For example, if our observations can influence distant quantum states, does this mean that consciousness, or at least the act of observation, plays a fundamental role in shaping reality? Observation. The cosmic observer effect is not without its skeptics. Many scientists argue that the effects observed in quantum mechanics are limited to the microscopic scale and do not apply to macroscopic systems like galaxies or stars. They point out that while quantum entanglement and superposition are well-documented phenomena, there is no evidence to suggest that these effects scale up to the cosmos. However, others counter that our understanding of quantum mechanics is still incomplete, and that the sheer scale of Webb's observations could reveal new aspects of reality that were previously hidden. For instance, the telescope's ability to detect faint signals from the early universe, such as the light from the first stars and galaxies, could provide clues about the quantum states of particles in those distant epochs. Interpretation. If the cosmic observer effect is real, it could mean that our understanding of the universe is fundamentally limited by our ability to observe it. This idea, known as the participatory anthropic principle, suggests that the universe exists in a state of potentiality until it is observed. In this view, our observations are not just measurements of reality, but active participants in its creation. This raises questions about the nature of existence itself. If the universe is shaped by observation, what does that say about the role of conscious beings in its evolution? Are we merely spectators, or are we co-creators of the cosmos? Speculation. The implications of the cosmic observer effect extend beyond physics into philosophy and even theology. If our observations can shape the universe, it challenges the idea of an objective reality that exists independently of observers. It suggests that reality is, at least in part, a construct of consciousness. This idea has been explored in various philosophical traditions, from idealism to panpsychism, which posit that mind or consciousness is a fundamental aspect of reality. The cosmic observer effect could provide a scientific basis for these ideas, bridging the gap between physics and metaphysics. For example, if our observations can influence distant quantum states, it suggests that consciousness is not just an emergent property of complex systems, but a fundamental aspect of the universe itself. This speculation is not without its critics. Many scientists argue that the cosmic observer effect is purely theoretical and lacks empirical evidence. They point out that while quantum mechanics allows for the possibility of observer-dependent reality, it does not require it. However, the advent of tools like the James Webb Space Telescope, which push the boundaries of observation, to unprecedented limits, could change this. As we delve deeper into the cosmos, we may find that our understanding of reality is more intertwined with our ability to observe it than we ever imagined. The void may indeed stare back, and in doing so it could reveal truths about the universe and ourselves that we have only begun to glimpse. Part 11. The Fractured Timeline. Webb was engineered to observe light, but it has revealed something far more unsettling. Structures that don't fit into our smooth timeline of cosmic evolution. Voids where light simply doesn't behave. Zones of silence where the rules of physics seem to break down entirely. These aren't small anomalies, they're gaping chasms in our understanding. Imagine staring into a region of space where stars seem to blink out of existence, or where galaxies appear distorted as if stretched by unseen forces. Webb's infrared eyes have captured these phenomena in unprecedented detail, and the data is as beautiful as it is terrifying. Interpretation. The universe is not tidy. It's wild, inconsistent, full of contradictions that don't just challenge our theories, they break the foundation of science itself. For centuries we built our understanding on constants, on numbers and principles we believed were universal. But Webb is telling us a different story. Take, for instance, the Hubble constant, a number that describes the rate at which the universe is expanding. Measurements from Webb and other observatories have revealed discrepancies in this constant, suggesting that the universe's expansion rate might not be uniform across all of space and time. This isn't just a minor discrepancy, it's a crack in the foundation of cosmology. The implications are staggering. If the Hubble constant varies, it means that the age of the universe, currently estimated at 13.8 billion years, might not be the same everywhere. Some regions of the cosmos could be older or younger than others, depending on how quickly they're expanding. This challenges the very idea of a cosmic timeline, a linear progression from the Big Bang to the present day. Instead, the universe might be a patchwork of different ages and histories, stitched together in ways we're only beginning to comprehend. Speculation. What if the rules we cling to are only regional? Imagine a universe where gravity behaves differently in one galaxy compared to another, or where the speed of light, long considered the ultimate cosmic speed limit, varies depending on where you are in space. Webb's observations of distant quasars and supermassive black holes hint at such possibilities. These objects, powered by the immense gravitational pull of black holes, emit light that travels billions of light years to reach us. Yet, the light we see doesn't always match our predictions. Some quasars appear brighter or dimmer than they should, as if the rules governing their emission have changed over time. What if light itself can lie? Light is our primary tool for studying the universe. We rely on it to measure distances, temperatures, and compositions of celestial objects. But what if light isn't always a reliable messenger? Recent studies suggest that light could be influenced by dark matter and dark energy, mysterious substances that make up 95% of the universe but remain invisible to our telescopes. If dark matter can bend light, an effect known as gravitational lensing, it could distort our observations, making objects appear closer, farther, or brighter than they really are. What if time folds and fractures in ways we never imagined? Einstein's theory of general relativity describes time as a fourth dimension, interwoven with the three dimensions of space. But what if this fabric of space-time isn't smooth and continuous? Webb's observations of ancient galaxies suggest that time might behave differently in different regions of the cosmos. Some galaxies appear to have aged more rapidly than others, as if their clocks are ticking faster. This could be a sign of time dilation, a phenomenon predicted by relativity, where time slows down in strong gravitational fields. But Webb's data hints at something even stranger, a fracturing of time itself, where the past, present, and future aren't neatly separated. The more we uncover, the clearer it becomes. The universe is far stranger than fiction has ever dared to be. Consider the concept of cosmic inflation, a period of rapid expansion that occurred fractions of a second after the Big Bang. This theory suggests that the universe underwent a brief but explosive growth spurt, stretching space faster than the speed of light. If true, it means that the universe we see today is just a tiny fraction of a much larger, unobservable cosmos. Webb's observations of the cosmic microwave background, the faint afterglow of the Big Bang, provide clues to this early era. But the data is full of puzzles, including unexpected temperature fluctuations and mysterious cold spots that defy explanation. As we delve deeper into the cosmos, we're forced to confront the limits of our knowledge. The universe isn't a simple puzzle to be solved. It's a labyrinth of mysteries, each one leading to another. But that's what makes it so compelling. Every time Webb uncovers a new contradiction, it's not a defeat. It's an invitation to explore further, to question our assumptions, and to rewrite the story of the cosmos. And in that journey, we're not just observers, we're participants, shaping the very questions that guide our understanding of reality. Part 12. The Edge of Knowledge. As Webb continues to push the boundaries of our understanding, an uncomfortable realization is taking root. With every photon it captures, every layer it reveals, it's not just observing the universe, it may be changing it. The James Webb Space Telescope, launched on December 25, 2021, has already begun to rewrite astronomy. Its infrared capabilities have peered through cosmic dust to unveil stars forming in the pillars of creation, and its deep field. Images have shown us galaxies that existed just 300 million years after the Big Bang. Yet, with each discovery, the telescope seems to pose more questions than it answers. Webb's observations have already challenged long-held assumptions about the early universe. For instance, the discovery of massive, well-formed galaxies in the first billion years of cosmic history has forced astronomers to rethink their models of galaxy formation. These galaxies, such as Glass Z13, are far more mature than theories predicted. The telescope's data suggests that the universe may have been more active in its infancy than anyone imagined, with stars and galaxies forming at an astonishing rate. This has left scientists grappling with the possibility that our understanding of cosmic evolution is incomplete. Speculation. What if science wasn't broken by Webb? What if it was never whole to begin with? What if this? Telescope didn't destroy our understanding, but finally revealed that we had none. The idea that our models of the universe are fundamentally flawed is not new. Throughout history, scientific revolutions have upended prevailing theories, from the heliocentric model of the solar system to the theory of relativity. Yet Webb's discoveries may represent something more profound. Not just a correction of our models, but a reckoning with the limits of human comprehension. Observation. The deeper Webb looks into space, the more it reveals about the universe's past. Its observations of the cosmic cliffs in the Carina Nebula, for example, have provided unprecedented detail about star formation, showing us the birth of stars in real time. Yet, these same observations have also raised new questions about the mechanisms driving stellar creation. The telescope's images of exoplanets, such as those in the TRAPPIST-1 system, have expanded our understanding of potential habitability beyond our solar system, but they have also highlighted the complexity of planetary atmospheres, leaving us to wonder how many of these worlds might truly support life. This leaves us with a haunting possibility. What else is hiding just beyond the edge of what we can see? Are we on the brink of a new era of discovery, or are we standing at the precipice of a cosmic abyss? The universe, as revealed by Webb, is both staggeringly vast and deeply mysterious. Its first images, such as the deep field of galaxy cluster SMACS 723, showed us thousands of galaxies in a single frame, each one a world of its own. Yet, the more we learn, the more we recognize the limits of our perspective. Webb's observations have already hinted at phenomena we cannot yet explain, such as the unusual brightness of some early galaxies, which defy current theories of stellar evolution. Interpretation. Perhaps the greatest lesson of the James Webb Space Telescope is not what it reveals, but what it leaves unanswered. Its discoveries remind us that the universe is not a puzzle to be solved, but an ever-expanding mystery to be explored. As Webb continues to probe the cosmos, it forces us to confront our own insignificance in the grand scheme of existence. Yet, at the same time, it affirms the human spirit of inquiry, the relentless drive to understand, even when understanding seems impossible. Speculation. What if the edge of knowledge is not a boundary to be crossed, but a horizon that forever recedes? What if the true purpose of Webb is not to answer our questions, but to teach us how to live with mystery? As we stare into the abyss of the cosmos, we are not just looking outward, we are looking inward, into the depths of our own curiosity and the limits of our imagination. And perhaps, in that reflection, we will find not only the universe, but ourselves. Part 13. The Final Countdown. The James Webb Space Telescope, Webb, has transformed our understanding of the universe, and its mission is just beginning. Over the next few years, it will delve deeper into the cosmos, unveiling more secrets and prompting new questions. With its infrared capabilities, Webb will explore distant galaxies formed mere hundreds of millions of years after the Big Bang, offering an unprecedented view into the universe's infancy. This journey is not just about expanding knowledge, it's about redefining it. Every image Webb captures is a portal to the past, revealing the universe's vast and enigmatic expanse. Each pixel of data carries the weight of cosmic history, with light that has travelled through eons of time, traversing unimaginable distances to reach Webb's delicate sensors. Webb's golden hexagonal mirror is an engineering marvel. Spanning 6.5 meters, it's the largest mirror ever sent into space, far surpassing Hubble's 2.4-meter mirror. Designed to capture faint, distant light with extraordinary precision, each segment works in harmony to focus light onto the telescope's advanced instruments. This technological symphony allows Webb to detect infrared light that has travelled billions of years, stretching wavelengths into visibility. The mirror's construction overcame monumental challenges, including the need for each of its 18 segments to align with nanometer-level precision, a feat akin to balancing a single grain of sand on the edge of a razor blade. The result is a telescope capable of capturing light from the earliest galaxies, which appear as faint smudges in the deep cosmic backdrop. Observation. Webb has already revolutionized our understanding of exoplanets and galactic formation. Its most profound discoveries, however, may still lie ahead. As it explores the cosmos, It will push the boundaries of human knowledge. For example, Webb's study of exoplanets like those in the TRAPPIST-1 system, 40 light-years away, could reveal atmospheric compositions hinting at life beyond our solar system. This system alone hosts 7 Earth-sized planets, 3 of which reside in the habitable zone where liquid water could exist. If Webb detects signs of water, oxygen, or methane in an exoplanet's atmosphere, it could rewrite the story of life in the cosmos. Webb's ability to analyze light passing through exoplanet atmospheres could lead to detecting biosignatures, chemical markers indicating life. The slightest dip in starlight as it filters through an exoplanet's atmosphere could signal the presence of molecules tied to biological processes, offering humanity its first tangible evidence of life beyond Earth. Webb's instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, detect the faintest signals from the farthest reaches of the universe. NIRCam's coronagraphs block out the glare of stars, enabling direct imaging of exoplanets. This tool has already allowed Webb to capture the first direct image of an exoplanet, P65426b, 385 light-years away, revealing a gas giant glowing faintly against the cosmic backdrop. MIRI, operating at temperatures just above absolute zero, captures mid-infrared light, revealing the chemical fingerprints of distant worlds. These instruments are portals to uncharted cosmic realms, each observation a step further into the unknown. MIRI's ability to detect long-wavelength infrared light makes it particularly adept at studying cold, distant objects, including the dust-shrouded nurseries where stars are born. Speculation. What if the universe is more than just stars and galaxies? What if Webb is a bridge to a new era of cosmic awareness? Its discoveries could upend theories about dark matter and dark energy, potentially revealing new physics like a fifth fundamental force. The standard model of particle physics, unchanged for decades, fails to explain phenomena like dark matter and dark energy. Webb's observations could provide the first clues to these mysteries, possibly leading to the discovery of new particles or forces governing the universe. One intriguing possibility is the detection of primordial black holes, hypothetical objects formed in the early universe that could account for dark matter. Webb's infrared sensitivity could uncover these elusive objects lurking in the cosmic background, reshaping our understanding of the universe's composition. Webb's journey to Lagrange Point 2, L2, 1.5 million kilometers from Earth, was a feat of precision engineering. At L2, Webb operates in perpetual cold, its instruments cooled to 267 degrees, enabling detection of faint infrared signals. The telescope's sun shield, a 5-layer structure the size of a tennis court, maintains these low temperatures, ensuring effective operation. This thermal stability is critical, as even the slightest temperature fluctuation could drown out the faint infrared signals Webb is designed to detect. The shield's delicate layers, each thinner than a human hair, work together to block the sun's intense heat, creating an environment as cold as the cosmic void itself. Launched on December 25, 2021, Webb's month-long journey to L2 involved a complex series of deployments, including the unfurling of its sun shield and the alignment of its mirror segments. This marked the beginning of Webb's scientific mission, a journey into the unknown, poised to transform our understanding of the universe. The deployment process was a choreographed ballet of engineering, with over 300 single points of failure, steps that, if unsuccessful, could have doomed the entire mission. Yet each deployment was executed flawlessly, culminating in the alignment of Webb's mirror segments to a precision of 50 nanometers, a feat comparable to aligning 2 grains of sand from opposite sides of the United States. Webb's first images, released in July 2022, were breathtaking. The deep field image of galaxy cluster SMACS 0723 showcased thousands of galaxies, some so distant their light took over 13 billion years to reach us. This single image contained more galaxies than Hubble observed in its entire lifetime. It also revealed gravitational lensing, where the galaxy cluster's mass warped and magnified the light of background galaxies, pushing the boundaries of our cosmic horizon. The gravitational lensing effect in this image allowed astronomers to peer even deeper into the cosmos, revealing galaxies that would otherwise be too faint to detect, objects that formed just a few 100 million years after the Big Bang. Webb's observations of the Carina Nebula provided a stunning glimpse into star birth. The nebula, a vast cloud of gas and dust, is a nursery for new stars. Webb's infrared vision pierced through the dust, revealing young stars and the intricate structures of the nebula, offering insights into star formation processes. The nebula's towering pillars of gas and dust, sculpted by the intense radiation of nearby stars, stand as monuments to the creative and destructive forces shaping the cosmos. These observations provide a snapshot of the dynamic interplay between gas, dust, and radiation that gives rise to new stars, offering clues to the origins of our own sun. The Southern Ring Nebula, a planetary nebula formed from the outer layers of a dying star, offered a different perspective on stellar life cycles. Webb's images revealed the nebula in unprecedented detail, showcasing the intricate shells of gas and dust expelled by the star. These observations provide a glimpse into the future of our own sun and the life cycles of stars. The nebula's delicate glowing rings bear witness to the final throes of a star, like our own, offering a preview of the sun's eventual fate billions of years from now. Webb's observations of Stephan's Quintet, a group of 5 galaxies, offered a window into galactic interactions. These interactions, which can lead to mergers and star formation, are fundamental to galactic evolution. Webb's infrared vision revealed the intricate dance of stars and galaxies, providing insights into the large-scale structure of the universe. The image of Stephan's Quintet showcases the violent yet beautiful ballet of galactic collisions, where gravitational forces entwine entire star systems in a cosmic waltz, sparking bursts of star formation and reshaping the cosmic landscape. As Webb continues its mission, it will explore even more distant and mysterious objects. Its ability to detect infrared light makes it uniquely suited to studying the earliest galaxies, formed just a few 100 million years after the Big Bang. These galaxies hold clues to the universe's infancy, allowing astronomers to test theories of galaxy formation and evolution. The first galaxies, born from primordial gas clouds, are thought to have been small, chaotic, and intensely star-forming. Webb's observations could reveal whether these early galaxies resemble our theoretical models or challenge our assumptions about the universe's early history. One of Webb's most exciting prospects is the study of exoplanets. With its advanced instruments, Webb can analyze the light passing through exoplanet atmospheres, revealing their chemical compositions and potentially detecting biosignatures. These observations could provide the first hints of life beyond our solar system. Webb's ability to detect trace gases in exoplanet atmospheres could also shed light on the diversity of planetary environments, from scorching hot Jupiters to potentially habitable worlds like those in the TRAPPIST-1 system. Each exoplanet studied adds another piece to the puzzle of planetary formation and evolution, helping us understand whether our solar system is unique or part of a larger cosmic tapestry. The search for life beyond Earth is one of the most compelling quests in modern science. Webb's ability to study exoplanets offers a unique opportunity to explore this question. By analyzing exoplanet atmospheres, Webb can detect chemicals associated with life, such as water, oxygen, and methane. The detection of these biosignatures would be a major breakthrough, providing the first evidence of life beyond our solar system. Even the absence of biosignatures in certain exoplanets could be revealing, helping scientists refine their models of how life emerges and under what conditions it might thrive. Webb's observations could also shed light on the mysteries of dark matter and dark energy. By studying the distribution of galaxies and the large-scale structure of the universe, Webb can provide insights into the nature of these enigmatic substances. This could lead to discovering new physics, potentially revolutionizing our understanding of the universe and its governing laws. Dark matter, which accounts for approximately 85% of the matter in the universe, remains one of the greatest mysteries in cosmology. Webb's infrared observations could help map its distribution by studying its gravitational effects on visible matter, offering clues to its elusive nature. The James Webb Space Telescope embodies human curiosity and ingenuity. Overcoming monumental challenges in its development, Webb is a technological marvel and a window into the cosmos. As it continues its mission, Webb will push the boundaries of human knowledge, challenging long-held theories and inspiring new questions. Its observations have already sparked debates about the nature of galaxy formation, the prevalence of life in the universe, and the fundamental forces governing the cosmos. Each new discovery is a testament to the power of human imagination and our unyielding quest to understand the universe. Conclusion. The James Webb Space Telescope has revealed a universe full of contradictions, challenging the foundations of science. It has given us a glimpse into the unknown, a chance to rewrite the story of existence. Webb's observations suggest that our understanding of cosmic evolution is incomplete, and the universe's history is more dynamic and unpredictable than imagined. The cosmos, as revealed by Webb, is a place of endless possibility, a tapestry woven with stars, galaxies, and perhaps even life beyond our wildest dreams. As we stare into the abyss, we must remember, the universe is a mystery, and as we stand on the edge of discovery, one question remains. What else is hiding just beyond our view? Perhaps Webb will uncover evidence of other universes or signs of intelligent life. Whatever lies ahead, Webb is our greatest hope for unraveling the mysteries of the universe. In the coming years, it will push the boundaries of our knowledge, revealing the hidden secrets of the cosmos. Each observation is a step further into the unknown, a testament to the human spirit of discovery. As we journey deeper into the universe, we are reminded of our insignificance and inspired by the possibility of discovery. The James Webb Space Telescope is our guide, a beacon of light illuminating the path to understanding.